If you haven't made your way to your table yet, if you could start making your way this way, that would be appreciated, just so we can stay on time tonight. So good evening, everyone. Welcome to USask Engineering's Capstone Design Showcase, proudly presented by Graham. My name is Mary Stewart-Torrey, and as a proud alumna of USask Engineering, I am excited to be your host this evening. Tonight, I am representing Graham, where I am a general manager for our Industrial Ag Division. Graham Construction is honored to support events like the Capstone Design Showcase that develop leadership, teamwork, and technical skills in future engineers. As we gather this evening, we acknowledge our connection to the land and to the people who built this country. Our nation's history makes us all treaty people. Graham's Saskatoon office, the USask Engineering, and our city are built on Treaty 6 territory and homeland of the Métis. It is important that we celebrate and share Indigenous ways of knowing. There is a place for all of us in engineering. Since the time of the treaties, Canada has welcomed diverse communities whose varied ancestry enriches this heritage, binding us more closely to a global community and the planet we call home. Through reconciliation, we will be the engineers the world needs and build strong foundations and relationships that will last as long as the sun shines, the grass grows, and the rivers flow. Graham Construction is excited to be part of this inspiring evening. The premise of the Capstone projects is much like Graham's culture of caring and collaboration. Whether it concerns our employees, company, clients, reputation, or each other, Graham people care. At Graham, we collaborate with each other, our clients, and our vendor partners. We walk the talk at all levels of the company and are active and caring contributors to the community in which we live and work. I believe many of the students presenting here tonight would say that those values align to working with their Capstone clients. You cared. You cared about your Capstone team members, your clients, and the problems presented as you work to complete the projects and develop the solutions we'll hear about tonight. It's this level of care that will make you the engineers our world needs. Tonight, there are 13 Capstone groups who will showcase how they've tackled a wide variety of real-world engineering problems for their clients. Watching these students highlight their work truly shows us the future of the engineering profession, and it is bright. For the students, this is the culmination of their undergraduate academic journey. Every course and every lab builds toward the Capstone Design class. Ask any engineering alumnus here this evening, they will remember their Capstone project. I would like to give a warm welcome and a note of appreciation to our sponsors for their commitment to celebrating this important milestone in engineering education. Graham Construction, our presenting sponsor. The Saskatoon Engineering Society, in partnership with APEGS, are the founding sponsor of the Capstone Design Showcase and helped launch the event in 2016. Mosaic is this evening's Capstone sponsor, and our award sponsors are Pinter & Associates is presenting the Environmental Impact Award, PCL has sponsored the Social Impact Award, the Best Consultation Award is sponsored by Hatch, and the alumni donors of the Engineering Advancement Trust are supporting the audience choice. Let's give a round of applause to our sponsors. This event is one of our favorites because our graduating students are showcasing the talents they will bring to Saskatchewan and beyond as USask engineers. We're excited to get to the student presentation soon, but before we do that, the kitchen staff from Prairieland Park has prepared a wonderful meal for us. So we will start with that, and I will see you again shortly. Hello and welcome back. If you are still eating, which I think everybody is, there is no need to rush. You can finish your meal as we get the official program started tonight. So please join me in thanking the kitchen for a wonderful dinner this evening, though. I would now like to welcome Akindele Odeshi, Associate Dean Academics of USask Engineering, to bring greetings on behalf of the college.
Yeah, good evening, everyone. On behalf of the College of Engineering, I say welcome. My name is Akindele Odeshi. I'm the Associate Dean Academics for the college, as you have been told. First, on behalf of the college, I would like to congratulate all of the students who have hand in sport in tonight's showcase. It takes discipline, creativity, commitment, and a lot of teamwork to complete this project. I hope you are proud of what you have achieved this year. Thank you to the family, friends, and college partners who are here to support and celebrate this student. This event is more memorable because of you. Each capstone design project begins with a problem that needs solution. These come from real-world clients. We are grateful to you for entrusting this work with our students. This practical engineering experience is a critical part of their degrees. Thank you as well to our faculty who have supervised this year's capstone groups. Not only the ones we see tonight, but all of the groups in this year's graduating class. I have no doubt your expertise has been invaluable. Our college is educating and training engineers needed in Saskatchewan and beyond. They work on projects that are growing the manufacturing, energy, agricultural, natural resource, and technology sectors. It is professional engineers who will lead and be part of the teams that will design, engineer, manufacture, construct, operate, and maintain this project in the decades to come. For our students, their USask engineering degree and their capstone design experience has put them on the path to discover and develop the solutions needed here and around the globe. Congratulations again to all of you on your project. The college is proud of your work, and we know you are well on the way to becoming the engineers the world needs. Thank you, and enjoy the rest of the evening.
Thank you, Akindele. As our evening unfolds, I would like to reiterate that this event would not be possible without our sponsors. And those sponsors, again, are Graham, the Saskatoon Engineering Society in partnership with APEGS, the Mosaic Company, and our award sponsors, PCL, Pinter & Associates, the Engineering Advancement Trust, and Hatch. Thank you all for your generous support of the College of Engineering and our students. I'd now like to welcome Trevor Tucker from the Mosaic Company to share a few words.
Good evening. My name is Trevor Tucker, and I'm the Senior Mine Manager at the Mosaic Kalonze Potash Mine. As a previous graduate of the U of S, I'm a geoengineer. I'm very excited to be here tonight and have the opportunity to deliver the welcome address for the Engineering Capstone Design Showcase on behalf of the Mosaic Company. Welcome to the students. This is a very exciting time for you. You're coming into the closing of the end of your fourth year, the Iron Ring ceremony, final design projects, final exams, interviews for engineering positions, and for some jobs, that's great. And soon to graduate and become engineers in training. Congratulations. As one of the judges, I had the privilege to preview the projects, and I'm amazed. It was a very impressive group of design projects. It's obvious that significant effort and innovation have gone into them. Welcome to the engineering faculty, Associate Dean Academics, professors, and advisors. Thank you for your dedication and commitment to the preparation of these future engineers. We are very grateful for your passion for education. Welcome and thank you to our project and showcase sponsors, without whom none of this would be possible. Speaking of sponsors, I want to take a moment to recognize the Mosaic Company. As a global leader in phosphate and potash production, Mosaic is more than just a name on the Regina Stadium. It serves customers in over 40 countries and employs over 13,000 people. Engineers from every discipline are involved in making Mosaic a very successful company. For me, Mosaic has provided me with over 28 years of employment and has given me the opportunity to complete my engineering degree and more recently my MBA. And for those of you that are wondering, I started working for Mosaic when I was 8. In closing, tonight allows us to celebrate the efforts and innovation of our engineering students. More importantly, tonight gives us a preview of the excellence that the next generation of engineers will deliver. And of course, the high quality of engineer that continues to graduate from the U of S. Congratulations to all the participants, and may your futures be as bright as the innovations that you've created. Thank you.
Thank you, Trevor, and thanks again to the Mosaic Company. So we will now get to what we've all been waiting for, the presentations by our senior engineering students. As you know, each student must complete the 495 Capstone design class in their discipline. They have been working for the past 7 to 10 months on a design project with a real-world client who had a problem to solve. Over the past month, each discipline has held its own Capstone presentation night, and the best design projects were invited to compete tonight. We are delighted to have representation from each program. We have 2 teams from civil, 1 from environmental engineering, 1 from geological, 3 teams from mechanical, 2 from the disciplines of electrical or computer engineering, and 2 from chemical. And there's 1 team each from engineering physics and general engineering. The groups have adapted their original Capstone design presentation for tonight's program. Each team will have 5 minutes on stage to tell you about their design problem and the solution they've developed. Along with bragging rights, there is $7,000 in cash awards up for grabs tonight, thanks to the generous support of our sponsors, again, who are Graham, the SES, APEGS, Mosaic, Pinter & Associates, Hatch, PCL, and the Engineering Advancement Trust. After the last group wraps up, the in-person audience and those of you joining us online will have a chance to vote for your favorite project, which will receive our Audience Choice Award. There will just be 5 minutes for voting, so please make sure you're ready with your phone to vote after the last group finishes up. So now it is time to get started. Please help me welcome our first team from Mechanical Engineering. The first Mechanical Engineering group can come up.
Good evening, ladies and gentlemen. Tonight, I would like to present to you our project on the 24-inch TerraSoft telescope optical tube assembly redesign. My name is Gavin Bendig, and together with me are Yona Kazito, Aaron Leppa, and Rylan Wilson. In 2012, the TerraSoft family donated their homemade 24-inch telescope to the University of Saskatchewan Physics Department. Unfortunately, the existing mount for the telescope ended up becoming inoperable. This led the university to purchase the PlaneWave L600 mount, which had a maximum payload capacity of 136 kilograms. Due to unforeseen factors, the the optical tube assembly that was donated had a weight of 157 kilograms requiring us to fully redesign the optical tube assembly whilst keeping the originally donated mirrors.
Now, in terms of goals for this project, our main goal was to mount the optical tube assembly to the newly purchased PlaneWave L600 mount. In doing so, we needed to reduce the mass of the optical tube assembly to be less than 136 kilograms. That was the limit of the newly purchased telescope tube assembly. And so then, further than that, once mounted, we needed to ensure that the new optical tube assembly did maintain optical alignment while in use and start trekking. And finally, the goal was to present the client with an updated SolidWorks model in lieu of manufacturing.
So our design process began with ideation as well as literature review, where we utilized a weighted decision matrix to eventually converge on what's called a Surrey truss design. The premise of a Surrey truss design is allowing the weight of each individual mirror to be equally opposed on around the optical axis, so each side is able to be deflect equally and maintain collimation regardless of its orientation. With that, we used what's called material indices to be able to finally define our materials. So with that, we maintained, we desired that it has low thermal expansion, it has a high strength to weight ratio, has a low cost and easy manufacturing. From there, we utilized ANSYS and SolidWorks models to eventually converge on a final design while utilizing topology optimization as well as finite element analysis to iterate and eventually come upon a final design. When we came upon a final design, we used FEA, thermal analysis, as well as modal analysis to get any sort of possible option that either direction or operating conditions that our telescope would be operating in. We used hand calculations to verify all of our individual analyses, and then we eventually converged on our final design.
So, as a result of the analysis, the final design features a Surrey truss combining carbon fiber rods for its high strength to weight ratio and aluminum plates for its ease of machinability. So in order to achieve optical alignment, we had to minimize deflections in order to, maintain optical alignment. So through various design iterations, we were able to arrive at a total structural deformation of 0.09 millimeters. So, because we were designing primarily to combat deflections, the tubes were oversized from a stress perspective. So because of that, the resultant safety factor was 25. So the final design came in around 88 kilograms, and which allows for an additional payload of 48 kilograms to be attached to the telescope.
Our final design has an estimated material cost of around $7,000, excluding manufacturing costs. This, when compared to other telescopes on the market of similar sizes, cost around $80,000 to $90,000, providing the university with substantial financial savings. With manufacturing to begin in the upcoming weeks, we plan to have this telescope fully operational and implemented at the university-owned Sleaford Observatory by August 2024. Where it will be located, it will be hooked up to the Skynet International Telescope Network, where students, astronomers, and any of the public can remotely connect and make their own stellar observations and acquire their own data should they see fit. I'd like to extend a special thanks to our client, Dr. Daryl Jansen, and our faculty supervisor, Professor Scott Noble, for their invaluable input and expertise through the duration of this project. Thank you, everyone.
Thank you, guys. That is incredible cost savings to do it for a tenth of what you could have done somewhere else. I'm sure the university thanks you for those savings. Okay, I would like to welcome up the second mechanical group now, automated measuring and cutting device for vacuum infusion materials.
Alrighty, hello everyone. We are another mechanical team and we are Calian Composites design team. My name is Jenna, this is Mason, that's Thomas, and that's Cole.
The background for this project is that our client, Calian Composites, is a composite-based manufacturer in Saskatoon. The primary manufacturing process they use is called vacuum infusion. How vacuum infusion works is a vacuum is used to pull liquid resin through tubing and into a mold to create the composite parts. This process uses single-use disposable tubing kits to create the molded parts. These kits consist of tubings of multiple sizes and lengths, and as of right now, they cut these kits by hand. They measure it out with a tape measure and use shears, and that is the problem. Doing this process takes roughly 7 hours per week to cut these kits, which drives high labor costs. Additionally, just doing this cutting doesn't foster employee development of skills, and that demands a solution. So the solution that Calian is looking for is an automated way to cut these vacuum infusion kits.
So during the design process, we found that there are three main functions that our final solution has to do. Feed, measure, and cut. So the four driving mechanisms, which you can see at the front of the assembly and in the top right, combine the feeding and measuring mechanisms into one component. So it's comprised of a 3D printed base, a rotary encoder, which is responsible for the measuring, a stepper motor, which feeds the materials, and a tension spring, which maintains adequate pressure, ensuring that slip does not occur. So 3D printed rollers are then friction fitted onto the shafts of the rotary encoder and stepper motor. The cutting component consists of a guillotine blade and a linear actuator. So how does this all work together? The four driving mechanisms shown at the bottom independently and simultaneously feed the materials into the cutter. Once the final segment has been reached, the linear actuator will push on the blade, cutting the materials, and the process will repeat until all the materials have been cut. We also have an acrylic safety box, which is clear and will cover all of the mechanisms, protecting the user from all moving parts. And finally, we have a Raspberry Pi microcontroller, which controls all of the parts at the same time.
Right, I'll touch on some of the benefits of our design. The biggest one is time savings. By automating this process, we can take the average kit cutting time from 30 minutes down to 5. This translates to an $11,000 cost savings in labor per year and gives our product a 3-month payback period. Additionally, our product is adaptable, and the modular design allows you to replace or add drivers and change the spools for whatever materials you're using, which allows our product to grow with the client. It also provides improved accuracy. The current method of cutting it by hand leaves a tolerance on the cut parts of approximately ±2 inches. Our prototype device, we've been able to get it down to ±1/2 inch, and we see further improvements by optimizing the coating, which Calian has kind of agreed to do for us. And last is improved safety, so you don't have to worry about using manual shears that are unguarded. Instead, our device is fully enclosed and complies with the Canada Occupational Health and Safety Guidelines.
So our client actually provided us with an impact statement, which I'll read now. The impact this device could have on our bottom line goes beyond just hours saved. Those hours can now be put towards innovation and testing, which allows us as a company to push the boundaries of the composites manufacturing industry. And that's everything we have. I hope everyone's enjoying the presentations and the food.
Thank you, guys. I appreciate that you talked about not just the engineering side of it, but the personal side as well, talking about safety, and then even developing the employees, that you recognize that the time that they would spend doing that cutting doesn't allow for development. So thank you for that, for thinking beyond just the engineering part of it. I will now introduce our third mechanical engineering group, the design of a supplementary wing fold system for a de Havilland CS2F tracker.
Hello everyone, my name is Evan, Sebastian, Bobby, and Katie, and we are presenting the design of a supplementary wing fold system for de Havilland CS2F tracker as part of the Department of Mechanical Engineering. Our client is the Saskatchewan Aviation Museum located here in Saskatoon up at the airport. They display a variety of planes with historical significance to the province of Saskatchewan. One of the planes in their collection is a 1960 de Havilland CS2F tracker as pictured in the lower right corner there. This plane was originally used by the Canadian Forces on aircraft carriers during the Cold War. It was then decommissioned and given to sold to the government of Saskatchewan, who converted it to a forest firefighting plane. Then it was given to the museum where it is used as a static display. One of the key features of this plane is its folding wings, which were originally designed to save space on aircraft carriers. To give you a bit of an idea as to how these wings fold, we have a picture of another tracker pictured here with the wings in the folded position. With the engines running, hydraulic power is supplied to the actuators, which begin to spread the wings as shown here. Finally, they reach the spread position when they're ready for flight.
This leads into the problem that our project sought to address. The Saskatchewan Aviation Museum required a design to fold and spread the wings of their CS2F tracker without the use of the aircraft's engines. Additionally, the design required the implementation of a fail-safe mechanism to prevent the wings from dropping in an uncontrolled manner in the event of any hydraulic failure.
The design that we developed to solve this problem builds upon hydraulic test ports that we located in the plane's landing gear wells. Our design utilizes a hydraulic cart that has a gasoline engine that drives a hydraulic pump, and the cart also has a hydraulic reservoir. This gives fluid to a flow divider valve that sends power to both of these test ports. This enables us to fold both wings simultaneously. Additionally, the design incorporates an electronic selector switch that allows the operator to select between folding and spreading of the wings from the cart. Without the addition of this switch to the design, 2 more operators would be needed to select between folding and spreading of the wings, and they would have to be in the landing gear wells of the plane next to those test ports. Finally, the design incorporates load holding valves in the form of pilot-operated check valves that ensure the safety of the museum staff who will be operating the design and any patrons who may be nearby, and they ensure that if hydraulic pressure is lost in the event of any failure, that the wings will not fall.
With this final design delivered to our client, there are a few steps that they will have to take in order to implement it. First, the museum will need to test the hydraulics that are inside the plane's wings in order to ensure that they are in proper working condition and to make any replacements that may be required. As well, since the museum is not a not-for-profit organization and they don't have current funds set aside for this project, they will need to fundraise the money that they need to implement it. They will then need to purchase and assemble the components, and our group has estimated that these components would cost around $13,500. We believe that this design provides the museum with a safe, efficient, and affordable method for folding and spreading the wings of the tracker without the use of its engines. Thank you.
Thank you, guys. What a neat project for a local museum. And I guess if we see a fundraising opportunity from them, we should all donate to it. Okay, I would like to now introduce our first civil group. We're doing the 24K Operations Tailing Management Area Expansion Dam.
Hello, everyone. Our project is the 24K Operations Tailings Management Area Expansion Dam. I'm Libby. I'm joined with Gabby and Andre, and our fourth teammate, Cream, couldn't make it tonight due to work commitments in Calgary, but we would just like to thank him. So a bit about our project. During the mining process, the targeted mineral is extracted, and the remaining materials, rock, soil, water, is considered waste. This waste is also known as tailings, and this tailings must be secured and contained to avoid any environmental impacts. So our tailings management area began operation in 2017 and is expected to operate until 2031. So to accommodate a raising in that pond elevation, we need to expand the current dam.
So to better understand our project, we wanted to know the geological story behind our site. To achieve this, we were provided with historical geological reports, borehole data, and CPT data from our client. By doing this, we were able to evaluate the ground conditions. Our newest layer is the Brenna Formation, which is a clay foundation, underneath the Whitemouth Lake Till, which is a thicker clay foundation underlain by a layer of silt, a layer of sand, and finally our bedrock, which undulates throughout the site. We are also given numerous lab test data to determine our material properties. Our main challenge with this site is that our thickest and weakest layer, the Whitemouth Lake Till, contained slick and slides. These slick and slides are areas of sheared material that are at or approaching their residual strength. To deal with this, we used our engineering judgment to come up with a phi of 15 degrees.
Once we understood the geology, we defined the alignment based on two considerations. First, the start point will be an extension of the existing structure, and the end point will be tied on the highest natural elevation in that direction. We divided the alignment into three segments for an easier analysis into GeoStudio. The final length is 927 meters, and we have high ranges of 1 to 10 meters. Now, Gabby will talk to you about the modeling part.
Our modeling process saw many iterations in order to meet factors of safety outlined by the Canadian Dam Association. To begin, our seepage modeling was used to determine the way the water would move through our structure. We used GeoStudio modeling for all the processes. Seepage was done at operation and flood elevations. This was then paired with stability modeling for both upstream and downstream conditions under flood elevation, operation elevation, seismic conditions, and rapid drawdown. Lastly, our consolidation modeling was modeled for 1 meter lifts during construction, and stability was analyzed at both 50 and 100% construction. As you can see on the screen, we have examples of our critical cross-section meeting factors of safety at 1.6 and 1.2, which Libby will discuss in our final design.
So just to kind of reiterate, the main challenge with this project is that we're essentially using a massive pit of jello as our foundation that's about 20 meters deep. So you can kind of get a picture of how hard that would be to stabilize a dam on. So our final design we came up with is a homogeneous clay core with a rockfill shell. We'll also install upstream and downstream berms as well as an upstream shear key. So this cross-section is just for our first segment, where the clay is the most critical and thickest, and then for our second and third segments, we can remove that upstream shear key and berm to save on material cost. So our final cost for just material and construction is $51.4 million, and we can source the rock and clay on site, and then the sand will have to be imported. As well, for construction, we recommend using 1 meter lifts per week and installing upstream and downstream drainage, as well as monitoring that construction using Skempton's B-bar method and installing piezometers. So in conclusion, we'd just like to thank our client for allowing us the opportunity to work on this very challenging and rewarding project, and thank you to our faculty advisor as well. Thank you.
Thank you. That is a massive project that I would love to build. We'll now welcome our second civil group, who is presenting the Battle River Bridge project.
Good evening, everyone. My name is John L. This is Cheyenne, Kareem, and John B. And this is the Battle River Bridge project.
The Little Pine First Nations community is requiring a river crossing to access their new wastewater treatment facility. The community is home to 975 people, and it is located 53 kilometers northwest of North Battleford and south of Saskatchewan Highway 16. The new wastewater treatment facility will decommission and replace the existing wastewater treatment lagoons. And to access these new lagoons, in addition to the bridge, the construction of an additional 4-kilometer road is required.
Our team evaluated various options and configuration to develop a cost-effective design with ease of construction. We considered NU and pre-stressed precast concrete girders for our design alternatives. We came up with 3 design alternatives for our project and use a concrete girder box for our all 3 alternatives. The first alternative was a 41-meter single-span bridge with a special single void concrete girders with a concrete slab deck on the top of it. One of the challenges we faced was procurement of 41-meter long girders, as well as transportation and erection of these girders during transportation. Additionally, the biggest problem we faced was the height of the abutment wall. In order to address these challenges, we developed the second alternative, which was a 42-meter 2 equal span bridge. However, this design introduced new challenges, which was having pier in the middle of the river. Ultimately, we developed the final design.
So the proposed design is a 45-meter 3-span bridge, which is constructed with 7 Saskatchewan box girder on each side. So we conducted the detailed design calculation in order to make sure that the Saskatchewan box girder will be able to withstand the applied loads on the bridge. And we've done this by following the standards from the Canadian Highway Bridge Design Code, as well as using SAP 2000 software to model and analyze the bridge. And furthermore, the road leading to our bridge is a gravel road, so we suggest using a gravel as a wearing surface to prevent any potential accidents. And in addition to this, our design includes a Type 4 bridge rail, which is extended by 5 meters on each end of the bridge to add any additional layer of protection for the traffic.
For the substructure components of our bridge, for the deep foundations, we originally looked at 2 different options. We started by looking at the continuous flight auger and then the steel pipe piles. We found during our cost estimating that the continuous flight auger piles were cheaper, but due to the cost of construction as well as availability of rigs, we elected to go with a concrete-filled steel pipe pile. For our earth-retaining structure, we looked at 3 options. We started with the Ministry of Highways standard design, and then we moved to a precast MSC wall with a steel grid. Finally, we looked at a lapped geotextile MSC wall with a lock block wall facing. We found during the cost estimating that the lapped geotextile with the lock block wall facing was the most cost-effective design.
We have divided the impacts associated to our projects into 3 categories of environmental, societal, and economical. For the environmental, construction of a new bridge requires consumption of high levels of energy, and it has carbon emissions. To account for that, we incorporated the use of prefabricated materials sourced from local manufacturers to reduce our carbon footprint as well as reduce environmental impacts. For societal and economical impacts, new infrastructure in the community and access to a new wastewater treatment facility, potential for economic growth and further development north side of the community, as well as more road access for local community members as well as farmers. Lastly, I would like to thank and acknowledge our faculty advisor, Jim Zacharak, as well as our client, Lawrence Lukey, for their support and mentorship. Thank you for listening.
Thank you. That's a big impact for a small community. And I loved that you talked about the use of local suppliers and looking at that was a big part of your project. So I'm going to ask the geological group to come up now, they will be presenting the Robert Service Way slope stabilization.
Good evening, everyone. Thank you for being here. I'm Reed. Beside me here is Colby, Emilio, and Garrett, and we're the geological engineering capstone design team, and our project was the Robert Service Way slope stabilization. So, a little bit of background. Robert Service Way is one of two main access roads into the city of Whitehorse in the Yukon Territory. Because of this, that means that a significant portion of the population relies on this route for their daily commutes. The problem with this is that approximately a kilometer south of Whitehorse, a portion of this road is built directly adjacent to the Whitehorse Escarpment. As you can see from the slides behind me, this is a fairly massive slope at about 60 meters in height and ranging from 35 to 45 degrees over its extent. This section of the slope is also prone to pretty significant failures that have been happening since the early 20th century. Since 2021, these failures have become more significant and more frequent, resulting in what we see in the bottom right hand of this slide. We see that during these failures, debris is crossing the road, which causes this road to be shut down for weeks or months at a time.
So when discussing the site geology present, there's three members that we need to discuss. First, there's a thin sand layer. Now this overlies a much thicker silt layer. Now the interface between these two layers is actually the root cause of a lot of the instability we see along the escarpment. There's a third layer. Now this is a colluvium layer. It's deposited parallel to the slope angle. Now colluvium is a mix of waste. It's basically sand, silt, and organic matter. So what's happening is that in runoff events like the spring melt or heavy rainfall, water is permeating through this sand layer, but it can't infiltrate the silt at an equal rate due to differing hydraulic conductivities. So this is effectively shooting water out of this interface into the colluvium. When colluvium becomes saturated, it fails, and it's using the silt as a sliding plane. You can see that in the mud flows shown above. So the June 2021 mud flow is actually a pretty good example of a textbook mud flow. You can see the source area, you can see the main track, which takes place as erosional gullies along the slope angle, or slope face, and then the depositional area. In the case of the April 2022 mud flow, that was the road, and that's what we're trying to eliminate with our alternatives.
Our group came up with three alternatives based on three main objectives. First, limit seepage onto slope. Second, stabilize superficial sediments. And third, lower the risk of shallow gravity failures. Our first alternative consists of the construction of an MSE wall. Our second alternative is regrading the slope and then installing geocell throughout the surface of the slope. And finally, our third alternative, and the one we chose, consists of the installation of a horizontal drainage system in the sand and silt interface. And additionally, the slope will be regrading from an existing average angle of 36 degrees down to an average angle of 30 to 31 degrees. After doing all of this, the slope will be hydroseeded to allow vegetation to flourish and limit the risk of superficial erosion.
Okay, so yeah, our drainage system was comprised of three different components. The first component was three sets of near horizontal drains that are placed at the sand silt interface to capture the seepage as it exits the slope. These drains consist of free draining granular fill as well as 24-inch perforated pipe to allow for fluid flow. Each set of horizontal drains will flow to a central downslope drain, which will carry the water safely down the slope. Since the angle of the slope is between 25 and 35 degrees, these drains will be filled with riprap to dissipate the energy of the flowing water. Once the water hits the toe of the slope, it will be passed under Robert Serviceway via culverts. In the figure there, it shows the culverts in red, the downslope drains in purple, and the horizontal drains in orange. In addition to our drainage system, we'll be regrading the slope, which will help lower the angle of the slope by 5 to 10 degrees, as well as remove much of the colluvium that is residing on the slope surface. We use slope W to model the effectiveness of our design, and by implementing the drainage system as well as regrading the slope, we increased the factor of safety against failures from 0.8 to 2.1.
Yeah, we just wanted to thank you all for listening to us tonight, and also give a thank you to our professor, Grant Ferguson, as well as Carly Isfield and Ash Hermanson with BGC Engineering for their advice.
Thank you, guys. That's another project with a massive impact for a lot of people. I'm now going to ask our environmental group to come up. They are presenting a remediation of an acid mine drainage impacted site.
Good evening, everyone. We are Kiba Consulting, and we are pleased to present to you our Capstone design project on an acid mine drainage impacted site. The location of our project is the Lorado Mine, which is located in northern Saskatchewan near Uranium City. Lorado is one of the sites a part of Project CLEANS, which stands for the Cleanup of Abandoned Northern Sites. The goal of this project is to remediate several abandoned mines in the area in a way that meets or exceeds regulatory guidelines. Acid mine drainage is a common and serious issue in abandoned mines. This process involves waste rock containing certain minerals getting exposed to air and water and forming acid. This highly acidic water causes heavy metals to be leached out of the waste rock, creating some extremely toxic environmental conditions. The goal of our design was to come up with a passive, low-maintenance system to remediate the flow of contaminated water from the Lorado wetland into Beaver Lodge Lake. It's important to note here that the pH of the wetland was found at 3.3, which is extremely acidic. Several substances of concern were found on site. However, only 4 were determined to be above guidelines, which include aluminum, manganese, iron, and most notably uranium. These substances are found to carry several human health and environmental effects, including organ failure, coma, and neurological issues, just to name a few.
So to remediate, we looked at a bunch of different options. We looked at a permeable reactive barrier, an anoxic limestone drain, a combo of those two, and a constructed wetland. By looking at our cost, our efficiency, and our long-term permanence, we decided on the permeable reactive barrier, or the PRB. So you can see our design here. It starts with 2 impermeable clay walls and a gravel pit. This will force the water into the reactive gate and through all those layers so it comes out clean to Beaver Lodge. We start with a geonet that's permeable. This will hold all our materials in. A 1-to-1 sand anthracite mixture will capture all the precipitates already in that outlet water to protect our next layer, mayonite. Mayonite is a new material. It's used as mineral phase change to target oxyanions, which is what our uranium is. Next is our biggest layer at limestone. This is going to use precipitation to target all of our cations. So precipitation will start first at a pH of 3 for the iron, 4 for aluminum, and finally 8 for manganese. 1 more sand anthracite mixture is going to capture all the precipitates that come out of that limestone. Finally, our last reactive layer is peat moss. So the pH is going to be around 11 after that limestone layer. So the peat moss will bring it down to about a 7 to 9 to make it more neutral. Finally, the system closes with 1 more impermeable geonet.
The total cost estimate to construct the PRB is roughly $3.2 million. The FreeQC model was used for geochemical analysis, which provided the chemical speciation of the SOCs. The results indicate a positive saturation index for uranium, meaning mayonite will cause it to mineralize. In addition to FreeQC modeling, our team completed lab work to test mayonite with the contaminated water from the site. the experiment being one of the first to test Mayenite for uranium removal. These results indicate a promising future for Mayenite in the remediation of AMD-impacted water. The photos on the screen show the initial and final state after 24 hours, which allowed for the full reaction between the Mayenite and the AMD-impacted water to take place. The efficiency of the PRB removes the iron, manganese, aluminum, and uranium to the percentages shown on the screen. The efficiencies remove the contaminants to well below the Saskatchewan Environmental Quality Guidelines.
So in summary, to target iron, aluminum, manganese, and uranium, we have designed a PRB system consisted mainly of limestone and Mayenite to remediate the acid mine drainage impacted site. It will cost $3.2 million and take less than 3 months to construct. Through this, we will see improvements in the water quality and the health of the ecosystem, decrease in toxicity and bioaccumulation, and the creation of local job opportunities. Additionally, when compared to the emissions generated over the operational lifespan of a mine, the emissions from the project is negligible. We would like to acknowledge our client SRC and our advisors, Professor Dr. Wanjay Cheng, for their help. Thank you for all your time and attention.
Thank you. I just want to say how incredible it is to see an all-female team. That was awesome. Okay, we've heard from about half of our teams, so we are going to take a quick little breather for a few minutes here. You can stretch your legs, get a drink, and I believe some dessert will be served as well. So we'll see you back in about 10 minutes. This is the 1-minute warning before we start with the next presentation. Okay, welcome back, everybody. We are going to jump into the next set of presentations here. I'm going to ask our electrical group to come up, who is presenting FlatSat testing system.
Good evening, everyone. We are the Electrical Engineering Capstone Group. I'm Riley. This is Colton, Cameron, Raph, and Nathan. And we are here to talk about the FlatSat testing system that we created for the RadSat SK2 project, which is Saskatchewan's second ever satellite.
So what is a CubeSat and what is a FlatSat? CubeSats are nano-class satellites with standardized units of 10 by 10 by 10 centimeters. Recently, the Canadian Space Agency has funded several CubeSat initiatives with the goal of designing CubeSats around Canada, giving grants to universities and undergraduate and graduate students. RadSat SK and RadSat SK2 are the two CubeSats that have been designed here at the University of Saskatchewan. The advantage of CubeSats is they're small, relatively inexpensive, and have design standards that make them approachable. FlatSats are a fundamental part of the testing process in which the components of the CubeSat are laid flat on a table. This allows easy access to test points. The problem with FlatSats is the limited documentation and market solutions. The FlatSat for RadSat SK1, as you can see on screen, used loose wires to connect boards together. Unfortunately, this caused a short and damaged critical components. RadSat SK and other undergraduate-led CubeSat projects have a lack of experience when it comes to proper testing, procedures, and practices, because the point of these projects is to give students experience. So a FlatSat needs to be designed that can mitigate some of the risks associated with undergraduate-led projects.
So, what are some of our goals for our system that we want to design? Our first and most important goal is to eliminate user error. Satellite PCB boards can cost up to tens of thousands of dollars per board. We require a system that can minimize the possibility that one of these boards becomes damaged. Our next goal is to expedite the setup and troubleshooting process. We want to make it fast and easy for multiple boards to be tested at the same time. Finally, we want our system to improve on the quality of testing that is currently done in FlatSat applications. This means enabling new ways to test that we couldn't before. Previously, it would have been impossible to measure 15 boards for power, current, and voltage at the same time. This is something we require our system to be able to do.
Okay, now we're going to discuss how exactly we achieve these goals using both a combination of hardware and software. So I'll cover hardware. This is our hardware solution. This is a custom designed printed circuit board designed in-house, which is shown in dark green, and we have the satellite boards, 6 of them connected in light green. So I'll go through some aspects of this design. Number one, we've eliminated all those loose wires that you saw earlier. We've routed hundreds of copper traces to connect all those PCBs rather than the rat's nest of wires. Number two, we have an end-to-end connection for testing up to 15 PCBs. And the reason why we mention that number is because Saskatchewan's next satellite, RadSat SK2, will have that many boards. And so what you can do is connect those green PCBs together end-to-end, and our software will handle the rest. Number three, we've designed protection circuitry. So this is an undergraduate project. You can do your best to design something, but once you plug in power, then it's in God's hands. And so, we've designed circuitry to protect the expensive components that you'd use in your design from itself. Lastly, we've also designed circuits to measure the amount of power consumed by these boards. So this is, of course, a satellite. It will be powered by batteries that are charged by solar cells. You want to make sure that however much power you think you're drawing from your battery to size it, you're actually drawing that much. And RadSat SK1 did not, unfortunately, meet that. And so these circuits will measure the amount of power, and they'll communicate that to our software solution.
Okay, for our software solution, we created an interactive user interface designed to reach our goal of a higher quality of testing. The main features of our FlatSat system are the real-time graph display that show a scope view of voltage, current, and power. Additionally, there's a custom satellite topology that shows instantaneous values of voltage, current, and power. Additionally, there's the log view that shows a system events that have occurred through a test. These events are under voltage, under current, over voltage, and over current. An example, as seen on the slides, is under current, where the logs have showed up in the log display. The system can also provide a historical session view of recorded values. Through these features, we expedite the testing process and improve its quality.
Thank you for your time, everyone. If you have any questions, please don't be afraid to ask any one of us. We'd love to talk to you.
Thank you, guys. That's one of the groups I got a chance to talk to ahead of this, and I had no idea what FlatSat was, so they did a great job of explaining it to me, so I appreciate that. Next up, we will have our computer group, who is presenting the low-tech IV pump.
Hi, everyone. We are here to discuss about the low-tech IV pump. My name is Nandish. This is Sam, Varun, and Daniel. So our goal, as you can see here, these pictures are taken by our client. He has past experience of working in Mozambique and knows that the current administration for IV is drip method, which is very inaccurate, inefficient, and time-consuming. So the scope of our project was to negate that and come up with an IV pump control system. We use an off-the-shelf pump and build the control system around it. Our design has to be low-tech, low-cost, specifically for low-income countries like Mozambique.
Okay, so for our design process. We have 4 major design constraints. The first one is that the cost must be below $300, as the typical IV pump can range from $500 to $3,000 or more. The second was that the parts must be easily sourced, so that if a component was to break down, they would easily replace it. The third one was an alarm system must sound when the bag is 80% empty.
This is an important safety feature as it wouldn't allow the pump to keep running when there's no fluid in there. You don't want to pump air into a human body. And the fourth one is that the backup power supply must power the system for 2 minutes. This is in response to the outages in Mozambique and their electrical grid not being as stable. We used alternative analysis to basically just decide which components would work best with a decision matrix. And for our design iterations, we mainly had trial and error, but we were able to complete our prototype.
So for our results, we got a cost down to about $124, which is quite significantly lower than what our target goal was, which was around $300. We also have the adjustable flow rate, so this, our prototype can go from 1 milliliter per hour to 1,000 milliliters per hour. We also have the buzzer system, alert system in place, so when the IV bag is about 80% empty, we actually shut down the system, and then you either would have to re-input or just shut down the whole system. For solving the power issue, we actually got a UPS module that can go on for 30 hours, so it doesn't necessarily always have to be plugged into the wall, so our prototype can be mobile. And you can actually see the block diagram of how exactly we achieve this.
Yeah, so moving forward with some future plans, we first want to implement an IV bag weight sensor for some active monitoring of our flow rate to verify our theoretical results. We also want to make a mount for the components, whether that be a PCB or something 3D printed, just to keep everything in place. Third, we want to add a pump lock to prevent any backflow when the IV is administered, just to make sure no blood can go back into the IV pump. And lastly, we want to open source the project just to make it available to any low-income countries that do want to use it, and as well to help with some of the hospitals not being governed by one specific body. They'd have access to it without having to organize throughout the country. That's all we have. I just want to thank our client, Dr. Adam McKins, and our supervisor, Chandler Jansen, and thank you for listening.
Thank you, guys. That was incredible. I was lucky enough to be in Mozambique and have experienced those power outages and heard from people there about how that really affects clinics and healthcare with the outages, so that's amazing. Thank you. Now we are going to call up the first chemical group who is presenting a waste heat recovery using heat pipe technology.
Okay, good evening, everyone. My name is Michaela Mankey, and I'm here with Paige Para and Kylie Hawkins. Together, we are Thermoflow Solutions, presenting our project on waste heat recovery using heat pipe technology. So as you all know, operating costs for energy is continuing to increase due to natural gas and carbon tax rates. That's why our goal with this project was to reduce the natural gas consumption within Nutrien Allen's potash mine to overall increase their mill efficiency and lower their natural gas CO2 costs. So the objectives with this project was to first determine the most optimum heat location for the heat pipe heat exchanger and to extract the most amount of heat, and then also find the best location to utilize that heat within the mill. We are then to find the best method to mitigate the corrosion associated with our design, perform an economic analysis, and then finally a safety analysis.
So we worked collaboratively with Solex Thermal Science and Econotherm to design a heat pipe heat exchanger unit that Allen could use in their mill. So heat pipes, as you can see, there's a diagram on the slide. They operate by using a hot stream to heat a working fluid inside the heat pipe. This fluid then vaporizes, and when it comes into contact with the cold stream, it condenses back down, and this continuous cycle is what makes the heat transfer happen. Nutrien was interested in heat pipes because of their redundancy, low fouling, and low pressure drops. So we decided to use potash dryer exhausts to heat crystallizer circuit brine. And we found that we were going to need 500 3-meter long heat pipes, 30 millimeters each in diameter to accomplish this. The unit itself would be 3.5 tons in weight and would have corrosion coating on the brine side of the line. So we completed a HAZOP to find some hazards, and we came up with some hazard mitigations. We found that temperature, pressure, and flow sensors should be installed with high-low alarms on both the exhaust and the brine lines, both to monitor heat exchanger performance and detect any hazardous conditions. A pressure safety valve should be installed on the brine line to prevent any overpressuring on the heat exchanger. The heat exchanger should be regularly cleaned and inspected to prevent blockages. A solids filter should be installed on the brine side just to prevent any possible solids from damaging the heat pipes. And there's actually an automated cleaning system on the heat exchanger to help remove particulate matter from the heat pipes. When this is activated, it would put a spike in particulate matter in the exhaust. So the scrubber brine following the heat exchanger should be increased to make sure that those particulates don't make it out to atmosphere. So this is a graph of our capital costing that we did. We found that we're going to need $720,000 in capital investment to make this project happen. The black line on the graph indicates the break-even line for Nutrien, where they'd be making their money back. We found that the payback period for the project is 3 years, but taking into consideration the time value of money, we found that the discounted break-even period is 4 years for the project. The net present value of the project is $900,000, and a present value index of 2 indicates that Nutrien will double the investment that they put in to this project over 10 years' time.
So this project, it has many benefits if it is implemented. Some environmental benefits would be that we'll have an energy savings of around 1 megawatt. So this is equivalent to around 113 meters cubed per hour of natural gas. And this will lead to a CO2 emissions reduction of around 1,568 tons per year. So to put that into perspective, that's around 350 Olympic-sized pools, so it's quite a lot. And some economical benefits. To Nutrien, it would be a more energy-efficient mill, so that'll lead to lower operating costs. And this is also a good positive publicity for them. And for a vendor, this is product exposure, which can potentially lead to additional sales. And for social benefits, this project is a good green corporate example, and it can also improve the air quality around the community around the mill. So in conclusion, we collaboratively designed an economical waste heat recovery system at the Nutrien Allen Potash Mill. So we got our natural gas savings down to 113 meters cubed per hour, and we reduced our CO2 emissions by around 1,568 tons per year. We completed a Class 4 economic analysis with a capital cost of around $720,000 and a PVI of 2. We identified many hazards and recommended different safeguards. And we also found that this project can have many positive impacts if it is implemented. So we'd like to thank our sponsor, Nutrien, and our vendors that we worked with, Solex and Econotherm, and also our profs, Lynn and Wank, for their help on this project. So thank you, everyone, for listening.
Thank you, ladies. Another project with good impact with not a huge amount of capital cost. We'll now ask the second chemical group to come up, who is presenting Net Zero Ethylene Plant.
So I would like to thank everybody for joining us this lovely evening. My name is Justin Hurtis, and I'm joined with my partners, Joel Schemenauer and Kaden Von Niesen. Together, we make up Carbon-Free Innovations, and our capstone project was to design a net zero ethylene production plant. So who exactly are we as Carbon-Free Innovations? We are an engineering design company that specializes in emitting CO2 emissions. we work in collaboration with the Chemical and Biological Engineering Department and with chief consultants Dr. Huey Wang and Dr. Lin. So as a company, we wanted to create a mission statement to help justify our impact and our goals as a company. So the environment is suffering from the significant increase of CO2 emissions to the atmosphere. Therefore, it is our responsibility to reduce these emissions. So now a little bit about our project. Dow Chemical came to us with this project that is in line with their goal to be path to zero. And this is to triple their production capacity at the Fort Saskatchewan mine and become the world's first net zero ethylene plant. So our main objective was to design an ethylene production plant first, and then to modify it to combat these emissions, which include Scope 1, which are the direct emissions, and Scope 2 emissions, which are the indirect emissions mostly associated with electricity. So why exactly is net zero important? Net zero is important due to climate change, the health due to poor air quality, the environment, especially safety, and the economy, and the ability to grow food as climate change is very detrimental and causes droughts. I would like to pass it off to Joel to go over our process design.
Thank you. First, the feedstock to the plant consists of ethane that contains 5% CO2. This is input into a cracking furnace where it's cracked at high temperatures and compressed, which gets sent down to the separation chamber where our final product, ethylene, is created. This first part of the process was created in Aspen HYSYS to simulate our CO2 emissions that are produced during normal operation. Our solution methods include method 1, where we use carbon capture units to capture the CO2 emissions from the furnace emissions and on the feed stream into the plant. Our second method uses recirculated hydrogen from the separation process, which is created as a byproduct during the reaction. Unfortunately, due to difficulties simulating this in our process simulation software, we're unable to accurately model the hydrogen fuel burning, and there was difficulties in regards to accounting for NOx gas creation as well from hydrogen burning, so we decided to move away from this method. As a result, we decided on our carbon capture units, and I'm going to pass it off to Kaden to talk a little bit more about those.
Yeah, so what we're looking at here is actually our process flow diagram of our dual carbon capture unit here, which tackles two feed sources, as Joel mentioned, the feed and the fired emissions from the heater. So this uses a monoethylene amine to use in our CO2 absorber, which has a high affinity, about 30 weight%, which is then extracted with a high pressure column in order to put into the ground or sequester. Some of the socioeconomic impacts, so we actually compared the methane costs per ton CO2 captured, which was around $139 per ton, and the actual nuclear or geothermal cost per ton CO2 captured at $116. So this $23 decrease in cost per ton allows us to change the carbon-free price of ethylene, which can make our carbon-free plastics much cheaper. So now just to go a little bit into our environmental impacts. One, this design captures 1.4 million tons of CO2 annually, which is attributed to about 320,000 cars off the road annually. It finally reduces the enhanced greenhouse effect as well that's affecting our planet, and reduced our carbon plant footprint. So now just some project conclusions. Why this project? As again, Dow mentioned this as well, but to become the net zero ethylene plant, ethylene is the key ingredient in polyethylene, which is in the plastics industry, so carbon-free plastics is part of the world's goal. What is our design? Well, we looked at two methods, method 1 and method 2, where method 2 is the hydrogen recirculation. We decided to go with method 1, the dual carbon capture on feed and fired heater emissions, which resulted in about 1.4 million tons CO2 captured annually. The indirect environmental impacts allows us to reduce the climate change by slowing down the temperature rise, as well as extreme weather events are reduced, so droughts and hurricanes are less frequent, as well as the temperature, or improving the air quality, so removing those criteria air contaminants, so less smog and less acid rain. Finally, why net zero? The world needs net zero because it is key to keeping the climate steady, saving nature, and making sure the economy grows in a green way for the kids of tomorrow. Thank you, Happy to take any questions after if you have any. Thank you.
Thank you, guys. Definitely something we will continue to hear more about with net zero as we move forward. Okay, the next group we have is the engineering physics group, who will be presenting the automated radioactivity measurements in aerosols. Over there.
All right. Hello, everyone. My name is Adam, and I have Michael on my left and John on my right, and you're gonna talk about ARMA, which stands for Automated Radioactivity measurements in aerosol.
So ARMA came about due to an issue at Orano Canada's uranium mill in northern Saskatchewan, the McLean Lake operation. Currently, technicians at the mill take aerosol readings to ensure that the radiation levels throughout the mill are within safe working levels. However, technicians taking these readings are both prone to human error and can be put at risk for overexposure to these aerosols. Aerosols such as radon progeny and long-lived radioactive dust, which are prevalent throughout the uranium mill when ingested or inhaled, can lead to some chronic health effects, such as lung cancer many years down the road due to the inhalation resulting in the aerosols depositing their entire radioactive dose over the entire lifetime of that specific aerosol. Therefore, a method to automate these manual readings is required. So at the mill currently, technicians take aerosol samples by blowing air onto a piece of filtered disc. This disc is then placed into a TriMet sample counter, and from that counter, technicians are able to infer information about the levels of the radiation throughout the mill. However, as one might imagine, it's quite a large mill, and this can soon become very labor intensive. So our solution had to reduce the amount that the technician had to interact with the sample taking device. Therefore, we replaced single-use filter discs with a continuous filter roll, as well as automating the calibration procedure for both the sampling pump and the sample counter, meaning that the technician only needs to interact with the design when they're replacing the filter roll.
So the way that we actually implement this automated design can essentially be boiled down to two main components. So each of them are mounted on two parallel CNC rails. The first of which is this component here, FRED. It stands for the Flow Retention Enclosure Device. It essentially moves up and down, creating an airtight seal around the paper such that air can be pumped through it, thus collecting a sample. This sample then moves to, I guess, Fred's wife, Rosa, which stands for the Rotational Operations Sequencing Apparatus. Now, if we look inside, we have this circular plate driven by a stepper motor. It has two apertures, the first of which has a removable source tray, which in our case contains americium-241 used for the calibration. The other, as you can see, images directly through to the paper, allowing us to collect a measurement on the sample. Now, we chose to use aluminum because Orano, when it comes to radiation exposure, adheres to a principle known as ALARA, which stands for as low as reasonably achievable. And we took this seriously in our design. So we chose to have these components hewn from single solid blocks of aluminum such that they attenuate the radiation thrown off by the americium source, therefore protecting nearby workers or persons. Now, the ultimate goal of this project, of course, was to automate the measurement of radioactive aerosols. And in this regard, we believe the system has succeeded with, as you can see, successful measurement of alpha radiation inside of ROSA. Now, we project a quadrupling of sample-to-sample efficiency with this system compared to the manual method. And when you consider the scalability of our solution, we project a 29-fold increase in the total sampling capacity at the McLean Lake operation. So while there is a lot of work to be done before this can be considered a commercially viable safety instrument, we believe we've laid a strong foundation for a more capable, reliable, and efficient way to protect workers from lifelong, life-altering chronic illnesses. Thank you.
Thank you. I will make sure I look for Fred and Rosa if I ever make it back to do work up at the uranium mines. Okay, we have our last group now from General Engineering, which will talk about the livestock lens.
Hello, everyone. Hope you're not falling asleep yet. We're the last team, so we'll try and make this fun. Cool. So we're the Livestock Lens team. We're a multidisciplinary team, and we represent the entrepreneurial Capstone class. So we've been working on a solution to automate the process of measuring cattle weight using artificial intelligence and computer vision. Now, this usually is a process that's both expensive and stressful for the cattle and the farmers. Using our technology, you can reduce waste, reduce the stress on the cattle, all the while helping farms become more profitable at the same time. We want to use AI to help build the farms of the future.
Right, so if you don't come from a cattle raising background, you're probably scratching your head wondering why this matters to you. The truth of the matter is that this really matters to farmers because they need weight data in order to be able to keep track of growth, health of their cattle, optimize feed for different pens, and project the weights for future buyers. But as you can probably imagine, weighing hundreds or thousands of large animals is not a painless process. Most of the farmers that we know choose only to do it a few times when they really have to because of how expensive it is. So not only does it take multiple people days to do, it also stresses out the cattle so much that they often won't eat for days after that. So it's just not feasible to do on a regular basis. Even though this is currently the best option for most of the farmers, this problem single-handedly costs one of the farmers we spoke to over $400,000 every single year. So this lose-lose situation leads to stressed cattle, stressed farmers, and higher beef prices for all of you.
All right, so let's take a look at existing solutions. Smaller farms use manual estimation techniques, which can be inaccurate. And then we have traditional methods such as a cage-like shoot scale that are so stressful that cattle don't eat for days. Newer technologies such as the walkover scales, for example, they're not widely used because of how unreliable they can be. So we began looking at our own solutions. Our first idea was to let farmers take pictures of the cattle using their phones. However, after a few talks with the farmers, we realized that what we needed was a fully automated process. Then we thought about using drones, but we quickly realized that they will also scare the cattle out. Lastly, we thought about using open area cameras, which can be situated around nearby water resources. This one seemed the most promising because it could capture a large area, but we quickly realized that gauging the distance and acquiring proper measurements would be too technologically difficult. So, in order to be successful, we knew our design must be fully automated, stress-free for both the cattle and the farmer, frequent, and reliable.
So based on these criteria, we developed our design, which uses an overhead automatic camera to image the cattle as they walk through lanes. These lanes are to be constructed nearby water resources so that the cattle intuitively walk through them and that their weight measurements can be taken without obstructing in their day-to-day activities. Once we have the images, they are processed using a 4-stage software program, which consists of distortion correction, animal detection, background segmentation, and finally the weight measurement using our artificial intelligence model. Using this model, we have been able to achieve an 85% measurement accuracy using only 2-dimensional images, and we have clear steps to improve this further. Additionally, you can see on the slide on the far right our physical implementation of this design, which also has a walkover scale. With this scale, we're able to get ground truth measurements to test our design and further develop it so we can make even better measurements.
So we have clear plans for commercialization. First, we want to improve our model, create a better data set, apply for funding, and then hopefully have a market viable software. Just to wrap things up, I just want to say thank you to all the people that helped us, as well as to you guys for taking your time listening. We'd love to talk to you guys after, so thank you.
Thank you, guys. I grew up on a cattle farm and know that there is a better way to do it than trying to get cattle to go through that chute. So that is everybody. So thanks again. I just want to say how amazing of a job everybody did here tonight, and maybe if we could just take a minute to show everyone our appreciation again. And now it is time for you, the audience, to have your say. We are going to open the audience choice voting. For our in-person audience, there will be a QR code on your table, and there should be one coming up on the screen shortly. So you can scan it with your smartphone. I assume everybody knows how to use a QR code. And you will see the full list of Capstone teams that have been here tonight. And for anybody online, you should see it on the screen as well if it's not there already. And again, there is no set criteria for this award, so you get to vote for whoever you want. It could be the best team, it could be someone you know on the team, your friend's team, your own team, and everyone here can vote. So select your favorite team and then hit the submit button to secure your vote. We will have voting open for 5 minutes. Okay. Well, I don't know. I don't have any technical abilities up here, so. But while we wait for the voting to happen and all the votes to come in, I would like to welcome up Dustin Archdeacon, a recent engineering graduate and alumni supporter from the Engineering Advancement Trust.
Good evening, everyone. Thanks, Mary. As Mary mentioned, my name is Dustin Archdeacon. I have recently graduated with a degree in mechanical engineering. So I was here last year, not competing because you guys are too smart for me, but it's a true privilege to stand before you as a representative of the Engineering Advancement Trust, or the EAT. And being a representative for the EAT means that I'm a representative for the engineering alumni community. First and foremost, again, one more congratulations to all of you. You did an amazing job. These are truly phenomenal, so one more hand of applause for the guys. It has only been one short year since I went through the Capstone experience. You may not think this now, but you will actually look back on these times and then the late night bonding sessions in a fond way. I'm not sure if you do now, but this will probably be the last time in your life that you'll have one friend working on a cattle scale and then another friend working on a radioactive tester. Like it's pretty amazing the type of projects that we get to work on in university. I would like to extend our heartfelt gratitude to the sponsors of this evening's event. Your unwavering support and dedication to the advancement of the USask engineers are deeply appreciated. The EAT takes immense pride in standing alongside all of the sponsors of this evening. Many of us gathered here tonight, including students, alumni, and faculty, have experienced firsthand the transformative impact of the gifts of the USask engineers through the Engineering Advancement Trust. Over the years, the EAT has contributed over $4 million, ensuring that the USask engineering students have access to better opportunities for learning and professional development. You may have noticed the red footprints around the college, and they're not for eating. I thought they were food, but they guide you to the various pieces of equipment and facilities made possible by the generous donations of the EAT alumni. These include essential equipment like the CNC lathe and mill in the Hardy lab, and in the other mechanical lab, the virtual reality lab software, and the development of the re-engineered first-year program, among many others. Beyond funding, equipment, and facilities, the EAT also enhances the student experience by supporting milestones events such as the Welcome Back Barbecue, the Hard Hat Ceremony, and the Capstone Design Showcase. Every student in the college benefits from the generosity of the alumni and the EAT. Our contributions go beyond tangible assets. They shape the future of engineering education. By investing in Engineering Advancement Trust, we empower the next generation of innovators, problem solvers, and leaders. Whether through funding equipment or enhancing academic programs or providing experiential learning opportunities, our support shapes the educational journey of the future engineers and consequently the trajectory of Saskatchewan and beyond. However, our involvement doesn't end with financial contributions. It's also about staying connected. The EAT offers numerous avenues for alumni to remain engaged with the USask engineering community. These connections enrich both our personal and professional lives, fostering a sense of belonging to something greater than ourselves. I urge each and every one of you, whether you're current students, soon-to-be alumni, or alumni, to consider supporting the EAT. Your support can be in the form of time, talent, or financial contributions. We warmly welcome your participation in carrying forward the USask engineering tradition of giving back. Together, we can ensure the legacy of excellence and innovation at the University of Saskatchewan continues to grow for generations to come. Once again, thank you so much, and the best of luck with all of to all the presenting groups, and as our audience choice votes are tallied, the EAT takes immense pride in supporting and sponsoring this award. Thank you very much.
Okay, thanks for those of you who told us about the voting. So we have closed the voting, and we're actually going to reopen it so that that duplicate is not there. So get out your phones again and re-vote, please. It'll stay open for another 5 minutes, and we will do this again. That award is at the end, so we will let voting stay open, but we're going to move forward with the rest of the awards. This is the exciting part tonight. So earlier this evening, the group of judges had evaluated each group's poster and heard a mini project pitch. Working through a comprehensive scoring system, they have chosen winners in the award categories that you will see on the screen, I think. After hearing all of these presentations and getting to chat with a few of the teams, I know that was not an easy task to do the judging. Judges, thank you for lending your time and expertise to this event. You are crucial to the success of the Capstone Design Showcase. I have had the award winners in my hand all night, and I have been wanting to look at it, but I haven't. I've saved it so we can all find out together. So our first award that we're going to do is the Best Industry Design Award, which is sponsored by Mosaic. So thank you to our judges, Ekinye Akinpelo, Ed Couture, Cam Schnitzler, and Trevor Tucker. And if Trevor could join me up here to present the award. give you this one first. The runner-up and recipient of $500 is the waste heat recovery using heat pipe technology. You guys can come up, yeah. Oh, yes. Yeah, if you guys just want to go onto this side. He's just in the middle there. Congratulations. And the winning team and recipient of $1,000 is the remediation of an acid mine drainage impacted site team. Congratulations. Those were great faces. I wish we had a camera on those. Thank you again, and thank you, Trevor. The next award will be for the Best Product Design Award, which is sponsored by the Saskatoon Engineering Society. Thank you to our judges, Edwin Edquist, Philippe Lepage, Derek Catterall, and Mark Patola. I would now like to invite up the SES President, Ekinye Akimpelo, to join me on stage to share a few words and announce the winners.
Good evening, everyone. I'm not announcing the award yet. I'm going to share 3 words. My name is Akini Akimpelo. I'm the Saskatoon Engineering Society President. SES is honored to be part of this program. SES, what do? We are 200 kilometers around Saskatoon. As an engineer registered at the Apex, you can join us. We organize leadership learning events. We organize networking events. We organize professional development events. And we give up to $500 in case you want to improve your career. Today, we're gathered here to celebrate the ingenuity, creativity, and dedication of our future engineers as they showcase their innovative projects and designs. This showcase is a testament of the hard work, determination, and passion of each student here that has poured out to this project over the course of their academic career journey. From conceptualization to execution, this project represents countless hours of research, experimentation, collaboration, accumulating to solutions to real-world engineering challenges. As engineers, we are tasked with solving some of the world's most pressing problems, from sustainability and environmental conservation to infrastructure development and technological advancement. This project is a display. Today, it reflects commitment to addressing these challenges head-on, pushing the boundaries of what is possible and driving possible change to our communities and beyond. So to the students and now our colleagues, I commend you for your dedication, perseverance, and innovative spirits. This project exemplifies the essence of engineering excellence and serve as a testament to the transformative power of engineering education. To the faculty, mentors, and industry, and also supporters, you've been guided and supported our students through their academic journey. We extend our deepest gratitude. Your mentorship, expertise, and encouragement have played a pivotal role in shaping the next generation of engineers and ensuring their success both in and out of the classroom. Lastly, as we explore and diverse the array of projects on display, let us all celebrate the achievements of our students. Everyone is a winner. And to reaffirm the commitment to excellence, innovation, and service to the society. Together, let us continue to push the boundaries of what is possible and inspire future generations of engineers to dream big, think boldly, and for engineers to be a better world. Thank you all. So the runners-up for the product design is waste. Sorry. The runners-up for the Best Product Design Award goes to Flat Sat. And the winner of the Best Product Design Awards go to AMA.
Thank you, guys, and congratulations to both of those teams. Now we have the Most Positive Potential Social Impact Award, which is sponsored by PCL Construction. And thank you to our judges, Kurt Sousey, Brennan Weiser, and Juniper Willard. And I would like to invite our sponsors from PCL Construction to join me on stage, and they can present the award. And the winner for the Most Positive Potential Social Impact is the low-tech IV pump. Congratulations to them as well. Next, we have the Most Positive Potential Environmental Impact Award, sponsored by Pinter and Associates. And thank you to our judges, Ty Van Camp, Sumith Kahanda, Glenn Kenke, and Clay Lanning. And I would like to invite Ty Van Camp of Pinter and Associates to join me on stage to present this award. And the winner of the Most Positive Potential Environmental Impact Award is the remediation of an acid mine drainage impacted site. A double win for them tonight. Congratulations. Watch out for those four. Okay, moving on to an award that is new this year, the Best Consultation Award, which is sponsored by Hatch. And a thank you to our judges, Stephen Huntley, Randy Shentag, and Arian and Kohi. And I would like to invite our sponsor from Hatch to join me on stage. Oh, great. And the winner and recipient of $1,000 is the waste heat recovery using heat pipe technology. Another double winning team. Congratulations. Is Carlene any? Oh, you've got it. Okay, great. We are going to move on to the Audience Choice Award, sponsored by the Engineering Advancement Trust.
You can do it.
Okay. Oh, this is like opening a Grammy or something like that. Okay, and the award goes to Net Zero Ethylene Plant. Congratulations. And just as an aside, this was a landslide win. Oh, you know what? We do. This. Sorry. Thank you to everybody tonight, those award winners, as well as all of the other teams. That was incredible. I am just blown away by how cool all of those projects were, what impact they would have. That was amazing. So I would just really like to, maybe we can give all of the teams a round of applause again. So this is really the end of our evening. I would like to thank faculty member Yen Han Lin and our external relations team for their hard work on this event. This is an incredible evening and something I'm just so honored to be part of tonight. And we would like to give another thank you to our sponsors, the presenting sponsor Graham Construction, the Saskatoon Engineering Society and APEGS, the Mosaic Company for being our Capstone sponsor, and then of course for our award sponsors, Pinter & Associates, PCL, Hatch, and the Engineering Advancement Trust. This evening would also not happen without our judges, of course our sponsors that we talked about, and you, everybody in our audience. So thank you for being here to support our student teams. But most importantly, thank you and congratulations to each team that participated tonight. You are now ready to be the engineers the world needs. And the engineering profession will definitely benefit from your knowledge. And of course, everyone is invited to stay and visit after this. And we just want to say on behalf of the College of Engineering and Graham Construction, thank you again for joining the 2024 Undergraduate Capstone Design Showcase.